Today, we are going to start with the new topic, that's diffusion. As you can very well see what exactly diffusion means, right? So what I'm trying to show in a normal layman's language, the blue color is diffusing with the pink color, and this is how the diffusion is taking place. So basically, the two colors are spontaneously mixing together into each other, and this is basically the process of diffusion, right? So this I'm trying to show with the help of two colors, but this diffusion take place naturally all around us. So this is what in normal layman's language the diffusion is. So in chemistry, we would define diffusion as it's a process of random movement of particles from the region of higher concentration to the region of lower concentration. So when there are, if we have a concentrated amount of gases in one beaker and we open the lid of that beaker, so the gases from the higher concentration, that means when they were in the beaker, they will start mixing out, they'll start moving out where they were more concentrated, and they will be moving to the place where there's a lower concentration of that particular gas, right? So that is what we call diffusion. So diffusion, I repeat again, is a process of random movement of particles from the region of higher concentration to the region of lower concentration. Now, we have often seen plenty of examples around us, which are, they are common daily basis, daily day-to-day examples. And the diffusion, they occur in all the three states. They happen in gases, they happen in liquids, and they happen in solids as well. But the solids, they very rarely take place, and it takes longer time for the diffusion to take place in solids, right? Now, these are some of the daily life examples which shows the process of diffusion. Often when our mother, she cooks food, so we can smell the aroma of food all around the home. So that is example of diffusion. Fragrance of the flowers in the garden spreading out. That is again because of the diffusion taking place of the fragrance in the garden, in the environment, in the air. Then tea bag immersed in the cup of hot water will again diffuse, and the water will change color. It will give you the taste, the flavor of the tea bag which you have dipped in it. That's all because of the diffusion. Then if somebody wears a perfume and enters the room, so, or if you spray the room refreshener, that is again the smell that spreads out. That's again a daily life example of diffusion. So this is all, these are your day-to-day examples of diffusion, right? Now, diffusion, let's prove through some of the experiments. Let's prove what exactly is diffusion. Now, here is one very common example here. Now, what do we have in this experiment? At the start of the experiment, we have taken two gas jars. This is one gas jar, and this is the second gas jar. And in the first, and both the gas jars, they're inverted over each other. The lower gas jar has got the reddish brown bromine in it, and we have a lid in between two gas jars. The upper one is being inverted over the lower one, and there's a cover in between, right? So unless we have this cover in between, both the gases, the air and the bromine, they are not mixing, or they are not spreading out, they are not diffusing into one another. But as soon as we take off that cover, we slides the cover slip from between the two gas jar, what happens? The bromine and air, they spontaneously mix into each other, and the air which was in the upper air jar and the bromine which was just there in the lower gas jar, now what happens? Both the gases, they diffuse evenly in both the gas jar. So this, they have now the lower and the upper gas jar, they both have the particles of air and the particles of bromine present in it. And that is what we see, that the uniform color of both the gas jar is basically the light brown. That is the end of the experiment observation. So this particular proves us that the diffusion do take place, and very fast in the gases. So eventually when they were separate out, they were not mixing, but when we give them the room to mix, they evenly and they uniformly mix together. Now, the diffusion has its take place at a certain speed, and we call that the rate of diffusion or the speed of diffusion. And the rate of diffusion is affected by two factor number one, we call it a temperature. Factor one is temperature, and the factor two is the relative molecular mass or the relative atomic mass. So these are the factors which are affecting the rate of diffusion, because these are the factors which are affecting the kinetic energy of the particles, right? And basically, when we increase the temperature, what happens? The kinetic energy of the particles that increases, and because the energy increases, so their movement becomes faster. When their movement become faster, definitely they are going to spread out, they are going to diffuse faster. So these are the two factors which we can prove that the diffusion depends on the temperature and on the relative molecular mass through experiments. So here is the first experiment which we are going to prove that the rate depends on the MR. So this is an experiment that proves that the relative molecular mass affect the diffusion rate. So in this experiment one, what do we have? We have a combustion tube. This is a combustion tube. We call it a combustion tube because it is open from both the ends and we can heat it properly. We can strongly heat this test tube, right? Now, in this particular experiment, what we are going to do is we are going to soak the cotton wool. We are going to take two cotton wools, and one we are going to soak in concentrated aqueous ammonia, and the other one we are going to soak in concentrated HCl. Now, the one which we are going to soak in concentrated aqueous ammonia is actually going to liberate the ammonia gas. Okay, it's going to give out the ammonia gas, right? So here that's giving out what? It's going to give out you the ammonia gas, whereas the other one is going to give us the HCl gas. So this side, cotton wool, the one which is dipped in concentrated aqueous ammonia solution, is going to give us the fumes of ammonia gas, and the cotton wool which is dipped in hydrochloric acid concentrated is going to give us the hydrogen chloride gas, right? So these two gases are being given by these cotton wools. Now, the precaution which we are going to take in this experiment is that we are going to insert both the cotton wool at the same time, so that these gases which are being diffused, which are going to come out of these cotton wools, they start diffusing at the same time period. So we are going to insert both the cotton wool, and we are going to airtight both the sides by putting a rubber bung or a cork to it, right? So what will happen now? This ammonia gas from this side and the HCl from this side, they start moving towards each other. The ammonia will be moving towards the right and the HCl will be moving towards the left, because we have a cork applied on this side. So gas diffusion is not in the opposite direction like this, right? So they will be moving towards each other. Now, depending on the speed, depending on the relative molecular mass, the ammonia's relative molecular mass, the atomic mass for nitrogen is 14 and the atomic mass for hydrogen is 1 times 3. So the MR for ammonia is basically 17, whereas the MR for HCl is 1, the hydrogen is 1, and for chlorine is 35.5. So when you sum up, so basically HCl has got an MR of 36.5. Now, their rate of diffusion depends on the MR. The higher the MR, the slower the diffusion. So when we compare the MR of the two gases, ammonia has got a lower MR. Having a lower relative molecular mass, its diffusion speed is going to be faster, right? It's going to be faster. That means when the two gases are moving closer to each other in each other's direction, ammonia is going to cover more distance as compared to your HCl, right? Because HCl's MR is greater. So ammonia, being lighter gas, is going to cover more distance, and you will be seeing a white color band close to the HCl end. This is a white color band, and this is being formed because when ammonia and HCl, they combine together, they give you a compound that is basically NH4Cl, that is ammonium chloride. So we get a white color band of ammonium chloride close to the HCl end because ammonia having a lower MR is going to cover more distance as compared to HCl, which is a heavier gas covering a lesser distance, and its diffusion rate is slower. So this experiment proves that on the basis of the relative molecular mass, the diffusion rate of the gases depends. Okay? The diffusion rates by which the gases are going to diffuse, the speed with which the gases are going to diffuse, that is different. The lesser the MR, so basically we can say the diffusion rate is inversely proportional to the relative molecular mass. Smaller the relative molecular mass, faster the diffusion rate is, right? And the heavier the gas is, slower the diffusion rate is. This is experiment number 2, and we call it a porous spot experiment. This is known as a porous spot experiment. Now, this porous spot experiment is a very special kind of a experimental setup, and this is the second type of experiment which again proves the same factor, that the rate of diffusion is based on, or it depends on, the relative molecular mass. Now let's see what is a porous spot experiment, because in this experiment normally been asked many a times in the form of an MCQs as well in the form of a theory question. Now, this is a kind of a setup where you have two beakers. This has two beakers. There is an outer beaker and there is an inner beaker, inner pot. And this inner pot, this is the outer pot. This is an outer pot, right? This whole pot is an outer pot, right? And there is an inner pot. We also have got an inner pot here. This is your inner pot. Outer pot and inner pot, they are separated by a porous lining or a porous layer. We call it a porous pot because this porous pot has got pores in it, right? This has got pores in it. So that is the reason we call it a porous pot. Or we can say that a beaker is inverted over the porous pot, right? So there's a beaker which has been inverted over the porous pot. Now, what happens in this experiment? We keep two different gases in these two containers. We have the nitrogen gas in the beaker, which is outside, and inside the porous pot, let's say we have a carbon monoxide. And the condition of this particular experiment is that this is an assumption, you can say, that the gases, they are just moving in and out of these two pots. That means they are not escaping out from here. They're not escaping out from either side. What is happening is that they are just diffusing from inner beaker to the porous pot and from the porous pot out to the outside beaker. And because of this movement, whichever the gas has got a lesser relative molecular mass. Now, for example, they have given us example of nitrogen in the outer beaker and carbon dioxide in the inside beaker. Now, let's see, what is the MR of these two gases. So nitrogen has got 14 AR, right? So multiply by 2, its relative atomic mass will be 28. Now, when we talk about the carbon monoxide, the carbon monoxide's carbon is basically 12. And when we add it to oxygen AR to it, that is again, basically that's 28. Now, because the relative molecular mass of both the gases are same, so definitely their diffusion speed is going to be same. Their diffusion speed is going to be same. Their rate of diffusion is going to be same. Now, the movement outside and inside the beaker is going to be same. Now, how are we going to see that the diffusion speed is same? Now, to this particular setup, there is a manometer being attached. This is a kind of a tube. This tube is actually filled with the liquid, right? So this is a liquid which has been filled in this tube, right? You can see as I'm showing, as I'm drawing the green line within the tube. So this is a green liquid which is being filled into it. Now, what happens if I have any other combination? Let's suppose if I'm not taking nitrogen and carbon monoxide, that is a case where both the MRs are same, so the diffusion speed is same. Now, let's suppose, let me take some other combination here. Now, instead of nitrogen, I have a hydrogen gas here and I have a carbon monoxide gas here. So hydrogen is in the outer beaker and we have carbon monoxide in the inner. So hydrogen's MR is basically 2, right? And carbon dioxide is 28. So which is a lighter gas? The lighter gas is hydrogen. So lighter gas is going to diffuse first. So what will happen? As I already told you, the diffusion will take inside and outside this beaker. So hydrogen being a lighter gas, it's going to diffuse inside through the pores of the porous spot. And the carbon monoxide, which is definitely a heavier gas, the carbon monoxide, which is definitely heavier. Why it's heavier? Because its AMR is 28. So it being a heavier gas is going to diffuse at a slower speed, right? So first what will happen? The hydrogen is going to diffuse in. Then after some time, the carbon dioxide will also start diffusing out. But initially only hydrogen is moving in. Now what will happen because of hydrogen is diffusing in? So there is a pressure being built up on the liquid in the manometer, and that will be pushed down. Because it's going to be pushed down, it's going to attain a new level in this manometer. So the water or the liquid in this manometer is going to be pushed down at a certain level, whereas on the other side of this manometer, the liquid is going to rise up. So that is going to be the new observation, that the water, we can label it as X level and Y level. So X level will be dropping, while why the X level will drop? Because hydrogen being a lighter gas will start diffusing in first, and that is going to create a pressure which is going to drop the level at the X, and the level X, its level will be dropping down, and from the Y end, its level will rise. Okay, so that is going to be observation. But this observation will be for a short time period, because eventually the carbon monoxide being a heavier will also start diffusing out. Once the complete diffusion of both the gases take place in outside beaker and in the porous spot, the liquid in the manometer is going to come back to its original place. So this observation, that is the dropping at the level X and the rise in the level Y, that is just for a short time until the hydrogen is diffusing. But once the carbon monoxide again start diffusing and they both evenly, uniformly diffuse, the levels are going to come back to their original position. So this is basically the porous spot, which again explains that the rate of diffusion, the speed of diffusion depends on the relative molecular mass of the gas. Now, in this experiment, they ask us to keep the different combination. Now, let's pick up a combination from here. Let's have the methane gas in the outer beaker, and let's have helium inside the beaker, inside the porous spot. If we have a methane in the outer and we have methane, if we have methane in the outer and helium in the inside porous spot, now what will happen? Now, helium being the lighter, helium's atomic mass, relative atomic mass is 2. And the methane's relative molecular mass is 12 plus 4, that's 16. So methane being heavier, it's going to diffuse later. So first diffusion of the helium will take place. So it is going to spread in the outer beaker. But after some time, the methane will start moving in. So because of this, for the helium is going to move out. So what will happen to the level X and to the level Y? Because helium is started diffusing out, so level X, the liquid at the level X is going to rise, because that's going to create the pressure in the porous spot. And accordingly, the level Y will drop. But as soon as the methane will also start diffusing in, and both the gases diffuse uniformly in both the beakers, the level X will come back to its original position, and the level Y will again come back to this original position. So this kind of explanation the examiner demands from us. They will be giving us different combination of the gases, and they'll ask what will happen to the level of the liquid in the manometer. Is it going to rise? Is it going to fall down, right? Or it will remain constant. If we have both the gases, like for example, initially we have seen we have nitrogen and carbon monoxide, and both the gases, their MRs were same, right? This was 28 and this was also 28. So when both the gases have the same MR, then the diffusion rate is going to be same. So we will say that the level at the X and the level at the Y remain constant. It is not going to be changed. So these are the examples. Now, one more thing I want to add over here. They often ask us if we have an air, and we know that air is a mixture. So the mixtures, they don't have any formula, and that's why we have a difficulty. In fact, we cannot calculate the relative molecular mass. But through experimental, through some experiments, because we know that in air, we have a certain percentages of different gases. Let's say we have 21% of oxygen present in it, right? We have 79% of nitrogen present in it, and we have approximately 0.03% of carbon dioxide presented in it. So on the basis of these percentages, it was calculated the AR of air, even though it's a mixture. So AR of the air, the relative molecular mass, the relative molecular mass of the air was taken as 28. So if they want you people to compare that, in the outer beaker you have an air, so remember the MR for air should always be taken as 28, right? So remember, if you have to make a comparison of air with, let's say, with the chlorine gas, so chlorine is basically 71. So air will be lighter and it is going to diffuse faster. Then because the chlorine is heavier, so it is going to take time to diffuse outside the porous spot. So remember, the air's MR, though it's a mixture, it's been taken as 28. Moving on, other kind of questions. So we have another question on the screen. Now, in this question, they have given us different gases, they have given us the formula, and the MRs are mentioned over here, and they have given short questions. And we have to answer these questions on the basis of the data given to us in the table. Now, the question number A part of the question: which two gases will mix fastest? So the fastest gases means that their rate of diffusion is going to be fast. Their diffusion rate need to be fast, right? And the gases which are going to diffuse faster are the ones with the lower MR, So they want us to give two gases. So let's see which ones are with the lower MR. This is one with the least MR. Then after this, we have the methane. So helium and methane are the answer for the first question. Now, the explanation which we have to give here, we will be saying that because the helium has the lowest MR, so its diffusion rate is going to be fastest. Then after helium, we have the methane. जिसका MR comparatively helium से थोड़ा ज्यादा है, तो वो भी उसका भी diffusion rate fast ही होगा. ठीक है? So these are the two gases which will mix fastest. Coming to the next part of the question, the B part, which gas will take least time? Least time means smallest time. They are going to take smallest time to escape. So again, when they were talking about the smallest time to escape, that means they are going to ask you which are basically the fastest gases, right? Which will be diffusing faster in lesser time period, right? In the smaller time period. Again, which gas? The one with the MR, with the smaller MR. So again, our answer is going to be helium, right? From the gas range. Coming to the C part of the question, would you expect chlorine to diffuse more slowly than the gases in the air, right? So in gases in the air, so maximum in what is the MR for chlorine? The MR of chlorine is 71. And when you talk about the air has got nitrogen, right, which is 79%, and the MR of nitrogen will be 28. Then we have some percentage of carbon dioxide, which is 44. Then we have, apart from that, we have oxygen, which is basically 32. So none of these gases have an MR greater than 71. So definitely the chlorine will be diffusing slowly as compared to any of the gases which are present in air, because chlorine has got more it has got more MR, and MR is inversely proportional to the rate of diffusion. So this is what you will be writing it down. This is what you will be writing it down in your explanation. Diffusion, right? Moving on to the question, part D of the question. An unknown gas diffuse faster than nitrogen, but more slowly than methane. So we have a nitrogen and methane. So they are saying that there's a gas which is moving faster than nitrogen, but slower than methane. So that means its MR is going to be in between nitrogen and methane. Its diffusion rate is slower than methane, but it's faster than nitrogen. So methane is basically how much? 12 plus 4, that's 16. Its MR is 16. And the nitrogen's MR is 28. So we have to look for a gas whose MR is going to be between 16 and 28. Do we have any answer over here? So nitrogen is 28 and methane. So which gas can be this one? None of the gases are mentioned over here in this, but we can think of some gas which is less than 28. Think of it. It cannot be chlorine, it can be hydrogen, or it can be, how about HCl? HCl is again your 36.5. What about the fluorine gas? What about the fluorine gas? Fluorine gas will definitely have lesser MR. Its MR is going to be 16 and 28. So fluorine can diffuse with the diffusion rate in between the methane and nitrogen gas, right? Okay, moving on to the next question, where again the MRs, how the MR is affecting the rate of diffusion. So let me read the question and highlight the key areas here. Now, the diagram below shows an apparatus for measuring the rate of diffusion of the gases at the constant temperature. So only one factor is affecting the rate of diffusion, and the temperature is kept constant. The rate of diffusion is measured in the terms of time taken for the water level to rise from A to B. Now, what is happening? They are just checking that how much time the water level from A will rise to the water level till B. Now, what is happening here in this particular diffusion plug in the this is plug, diffusion plug. That means this has a pores and the gases can diffuse out of this plug, right? So this is kind of a cork they have, but this has pores in it, right? So any gas can diffuse out of it. Now, in this graduated tube, they have a gas here. They have kept a gas in this. Now, what is happening? This particular part is again porous. This again part is a porous. And what is happening? The gas which is present in the graduated tube is diffusing out. And because it's diffusing out, so the vacuum is being created and the water is sucked in, right? So water has been sucked in, and they're just noting that how much time it's taking the water to be sucked from A to B, for the water to travel from A to B. So they have a different combination of gases here. The first gas is basically carbon monoxide. So the gas can be carbon monoxide, or it can be chlorine, or it can be methane, or it can be oxygen. So they have the 4 set of gases. So they have performed basically the 4 experiments just to check what time it's taken for the water level to rise from A to B. So that depends on the diffusion rate of the gas. The gases which are going to diffuse faster, the water level will rise up faster. The gases which are going to diffuse slower, there the water level is going to rise up at much slower pace. So now let's see, that is all about the experiment. And here they have the different gases and the time it took for the water to travel from point A to point B. Now we know the carbon monoxide. Carbon monoxide is basically, its formula is CO, and its MR is 12 plus 16. That's basically 28. That's an MR for carbon monoxide. Chlorine is Cl2 and its MR is 71. Methane is CH4 and its MR is 12 plus 4, that's 16. And oxygen is basically your O2, and oxygen's MR is 32. Now we know that the gas whose MR is the most is going to take maximum time. So we have a gas here that is basically the chlorine. The chlorine's MR is highest, so it's taking the maximum time to travel. And out of these 4, methane has the least. It has the least MR, and that is why it's taking the smallest time. It's taking the least time to travel the water. It's taking the water to travel from point A to B. You can see only 90 seconds it's taking. Whereas the rest of the gases, they're taking 119, 190, 90, and 127. So if it is taking lesser time, that means its diffusion rate is faster because its MR is less. So that is our understanding from the table, right? So now let's see what are the questions and how we can solve these questions. Okay, so let's see. Let me leave the MRs on the screen so that we can answer them quickly. The question number A part of the question is that what do you mean by diffusion? So we'll define the diffusion. It's a spontaneous movement of the particles from the region of higher concentration to the region of lower concentration. Now, which gas diffuse slowest? That means its MR is highest. Its MR is the max, right? And because we say that the rate of diffusion is inversely proportional to the MR. जितना MR होगा उतना ही rate of diffusion faster होगा. तो MR किसका ज्यादा है 71 और उसका rate of diffusion जो है वो slow है, इसीलिए वो ज्यादा time in seconds ले रहा है A से B तक वाटर को आने में, क्योंकि वो डिफ्यूज आउट स्लोली हो रही है. ठीक है, वो बाहर निकल रही है देर से. Name a gas that will diffuse slower than any of the gas shown in the table. Now, in the table, we have got 4 gases. We have got carbon monoxide, chlorine, methane, and oxygen, and their different MRs also mentioned, right? So they're asking us to give us an example of any other gas, okay, which is basically which has name a gas that will be diffusing slower than the gases which are mentioned here. So this is the one which we have considered as the slowest, because out of these 4, iska MR जो है वो highest है. So that means 71 से ज़्यादा MR वाली हमें कोई gas चाहिए. So we can have the bromine gas, because bromine gas, the AR for bromine is 80 times 2. That is going to be approximately 160. So 160 is more than 71. Similarly, we can have hydrogen bromide gas. So its MR is going to be 1 plus 80, which is equals to basically 81. Then we can have any other gas, right? Whose MR, we can guess any other organic gases whose MR is more than 71. So these are the 2 examples which I have in mind right now. Now, coming to the next part, that's the D part, suggest a reason why hydrogen chloride gas cannot be used in this experiment. This is a very good question. Now we need to understand that this particular experiment is based on the water diffusing from level to A to B, water moving from level A to B, and the gases diffusing out. Now we know that the HCl gas is water soluble. It's water soluble. So what will happen? The whole setup has water inside it. So the gas, what will happen here? The water is going to reach the gas. The gas is there in the graduated tube, right? So if the HCl gas is here and water is somewhere here, the HCl gas being solved in water, it is going to dissolve in water rather than it will diffuse out. So what will happen? There are chances that the HCl will dissolve in water rather than diffusing out. So that is why this particular experiment is not suitable for the gases which are soluble, and one of such gases is hydrogen chloride. Coming to the E part, suggests why ethene is expected to take the same time to diffuse as carbon monoxide. The formula for ethene is basically C2H4. It's C2H4. So if we have the formula for ethene as C2H4 and we have the formula for carbon monoxide as CO, let's calculate their MRs, right? So ethene is 12 into 2, that's 24 plus 4, that makes it 28. And over here, we have 12 plus 16, that's again 28. So these both gases have the same MR, and that is why they'll be taking the same time to diffuse, because the MRs are same. I hope all these concepts are clear, and we are only possible to perform this experiment because the temperature is kept constant. On the screen, we can see another past paper question. Let's solve this past paper question. And this question says the following apparatus can be used to measure the rate of diffusion. And what are they doing? They are applying the constant pressure through this plunger on the gas syringe, right? And over here, they have a metal foil and there is a hole in the foil. There is a hole in the foil, right? And there's a gas in the gas syringe, and because we are pressing the plunger, so gas is forced to pass through this hole out from here, right? So gas is moving out, it's diffusing out. So that is the whole experiment about. Now they're asking, the following results were obtained. They have the two gases. They tried the experiment one with the nitrogen at 25 degrees Celsius. That's experiment one. Similarly, they tried the experiment two with the chlorine, and no temperature and stuff is given, right? And the experiment three was done again with the nitrogen, but at the different temperature of 40. Let's take it. Now, the diffusion rate, let's compare the two experiments of nitrogen itself. The two experiments of nitrogen are basically are performed at different temperatures, right? The two experiments of nitrogen are performed at different temperature. Now, this experiment actually proves that this experiment proves us that the rate of diffusion also depends on temperature. And the temperature, what happens when we have increased temperature? So what happens? The kinetic energy of the particle increases. And because the kinetic energy of the particle increases, so the particle movement become faster. Now, when the particle movement become faster, the diffusion rate is again going to become faster. Diffusion rate will be fast, right? So this is how we use the kinetic theory of particles to explain this particular factor of temperature, how it's affect the diffusion rate. Now, when we can see this experiment, when it is being conducted at 25 degrees Celsius, it's taking the rate of diffusion is just 1 cm cube per minute. But when we increase the temperature to 40, now it's diffusing 1.05. The more gas is diffused out of this hole, the more gas is being diffused out of this hole, right? And that is basically 1.05 per minute. So here we can see that the temperature is a factor which is making the nitrogen gas having the different diffusion rate. Now, explained by the nitrogen gas diffuses faster than chlorine. The one of the reason is that now we can see it here, whether at the room temperature or at 40 degrees Celsius, the diffusion rate is definitely faster here. The reason is the nitrogen has an MR of 28, whereas the MR for chlorine is 71. Chlorine is Cl2, that's 35.5 into 2, which is 71, right? So because its MR is less than, the nitrogen MR is less than chlorine. So that is why even though the temperature at different temperatures, its diffusion rate is going to be much higher, much faster than that of chlorine. Explain why the nitrogen gas diffuses faster at different temperature, at a higher temperature. What is happening? This is what I explained. The kinetic energy of the particle is more, the moment is faster, diffusion rate is faster. At a lower temperature, the particles, they possess the lower, okay, they possess lower kinetic energy, hence their movement is going to be slower, and because the movement is going to be slower, so diffusion rate is going to be slow. So that is what we will be they're expecting us to explain. This is the same experiment which I've explained before, and this is given in the form of a question. Let's do it step by step. I'm just reading it out because I've already explained this question, so we'll go at a faster rate. So they have the concentrated ammonia solution gives off ammonia gas that we're already aware of, whereas the concentrated HCl end is going to give you the HCl gas, right? Now, ammonia and the hydrogen chloride gas are both colorless. ammonia react with HCl to give you a white solid ammonium chloride. Now the pattern is set up as follows. These are the two cotton wools. This has been soaked in HCl. There's another cotton wool soaked in concentrated aqueous ammonia, and then they have been inserted at the same time at both the ends of the combustion tube. Now, because we know that the HCl is basically 36.5, its MR is 36.5, because 1 plus 35.5 will give us 36.5. And ammonia's MR is basically 14 plus 3, that is basically 17. So ammonia, that's 17, sorry. So ammonia having a lesser MR, will be diffusing faster. So ammonia is going to cover a greater distance because it's almost half its MR, whereas the HCl is going to cover a lesser distance. So we will be observing a white color band there at point A, right? So they're asking, write a chemical equation for the reaction of ammonia and HCl. That is that you will learn when you will be doing the later part of the syllabus, how to write down the equation. But I'm just supporting you here. So we have ammonia plus HCl. They combine together to give you ammonium chloride. And they've already mentioned above in the question that the ammonium chloride is a white band which is being formed. So this is basically your solid, right? Now name the process by which the ammonia and hydrogen chloride gases move in. So we know the answer is basically the process is known as diffusion. Now moving ahead to the next part of the question, the next part and the last part of the question says that at which point A, B, C, or D does a white solid form, that I've already mentioned, because ammonia has got lesser MR, it's almost half that of HCl, so it will be covering more, almost a 3/4 of the test tube, and 1/4 will be covered by HCl. So we'll be seeing a band somewhere around A. Okay, the solid form somewhere around A. So that is what we know about it. Now let's move on to the next part. So this is the last part of that particular question we have seen before. So if this combustion tube, if the same combustion tube we have, whatever, okay, this combustion tube which we have seen on the previous slide, if this combustion tube, they're asking if it is experiment is repeated but at higher temperature. Let's see, the previous experiment A was taking place at 25 degrees Celsius, and now what we are doing is now we are increasing the temperature from 25 to 50 degrees Celsius, right? So what will happen? Will the diffusion of the two gases will be different this time? No, it is not going to be different, but both the gases, their diffusion rate is going to increase. So what will happen to the experiment? That we will be able to see that white color band forming at a faster pace, because both the gases will be diffusing faster. The same question in one of the past paper question, they have formulated in a way that what will happen if this same experiment combustion tube is kept in oven, right? So if you're going to keep it in oven, that means we are actually repeating the experiment, or we are keeping this combustion tube at a higher temperature. So you will be giving the same response in that also, that when you're going to keep the combustion tube in an oven, so what will happen? The rate of diffusion, because the temperature is being increased, so the both the gases are going to diffuse faster, and we will be seeing the result, the product being formed faster, because one of the factor to affect the rate of diffusion is temperature. Okay, this is the last question of today's video, and it's again a past paper question. The diagram below shows a simple experiment on the speed of diffusion of the gases. So we have the experiment one, diagram one, we have the diagram one, and we have the diagram two, right? Now in diagram one, let's study the diagram one. What do they have? They have the inner porous spot, and they have inside the porous spot their air, and outside also definitely there is no other beaker, and we have the air outside also. So because inside and outside both are air, so diffusion rate will be same because we have air here. So will we be seeing any difference in the level of the liquid, colored liquid? No, because both the gases or both the substances are same, so their rate of diffusion will be same. So hence the level of the liquid will remain same. throughout the experiment. Now, they're asking you to complete the following explanation as it's done in the diagram 1. Now, the explanation for the diagram 1 is given to you over here. There is an air inside and outside the porous pot, so the rate of diffusion of the air into the pot is same as the rate of diffusion of the air inside and outside the pot is same. The pressure inside and outside the pot is also going to be same. So the colored liquid is at the same level on each side of the tube. There will no change in the level of the colored liquid. Neither it's going to go down at one end nor up, because both the gases are diffusing at the same rate. Now, what they have given us a diagram 2. And in diagram 2, they're expecting us to write down the similar explanation over here. Now, let's see what they have in diagram 2. In the diagram 2, they have air inside the porous pot and they have hydrogen outside. Now, we know that, as I have told you previously in the same video, that air, though it's a mixture, but we considered the MR of air as 28 and hydrogen is taken as its MR is basically taken as 2. So being reduced, having a lesser MR, what will happen? The hydrogen is going to move inside the porous pot because its MR is less, so its rate of diffusion is faster. So what will happen to this level? And let's label them as X and Y. So X level will fall down. The colored liquid at the X level will fall down, and at the level it's going to rise up, right, initially. But very soon after the hydrogen has been diffusing in, soon after some time, the air will also start diffusing out. Now, as soon as the air will diffuse out, then after some time, both the gases have uniformly mixed together. Now, once the gases have uniformly mixed together, they have, right? So what will happen? The level at X will come back to its original position, and the level at Y will come back its original position, because both the gases have now uniformly mixed together. So this was the experiment 1 and explanation for diagram 1 and for diagram 2, right? Now let's move on to the next slide, and that says that is about the diagram 3. Now, in diagram 3, we have the combination of gases in the inner and the outer beaker is that inside again they have air, right? And outside they have carbon monoxide. Now, carbon monoxide's MR will be taken as 44, and air's MR is the same as I've explained before, it's 28. So air having a lower MR is going to diffuse faster into the outer beaker. Because of this, if we call it level X and level Y, because of this, the pressure will be created and the X level will rise and the Y level will fall down. But after some time, what will happen? After some time, the carbon dioxide, even though it's heavier, but after some time, it's going to diffuse in. And both the gases will eventually mix together uniformly. When they'll mix together uniformly, then what will happen? The level of the X will come back to its own position, and similarly, the level of Y will come back to its own position, because the complete diffusion of the gases has taken place. And that's all about the topic diffusion. And inshallah, we'll be covering another subtopic or another topic in the next video.